All right, hello everyone. So I'll be giving a talk about the MineDOJO and Voyager. Unfortunately, the authors on those papers weren't uh, able to make it to ICCB, so I'll be presenting this paper on their behalf. So since it will be weird to just use the pronouns like they, them for the rest of the talk, so I'll just use the pronoun like we and I, even though I'm not part of the projects. Okay, so first paper that I'm going to present is MineDOJO, and then this is an open source framework for autonomous agents to perform wide range of open-ended tasks. And the second paper that I'm going to talk about is a language-based agent that is built on top of MineDOJO. I hope the video plays. And yeah, these are some of the example videos that you can showing what you can do on this framework. So MineDOJO is built on top of a popular online game called Minecraft, where you are placed in a blocky environment and you can explore hard resources like wood, iron, and build items like swords, axes, and you can hunt animals and kill enemies. And also users can build houses, ride, landscape, and the things that you can do is almost unlimited. And it allows the users to express their creativity. And MineDOJO is an extension of Minecraft that consists of three major parts. The first one is the open-ended environments that includes ocean, desert, ice caps, underworld, and many interesting words. And the second one is internet scale knowledge that is sourced from YouTube, Wikipedia, and community discussion, specifically subreddit, Minecraft subreddit. And the third one is a generalist agent that's developed with the simulator and massive data. So here is an example gallery of interesting things that an agent can do in Minecraft. And they consist of like defeating monsters, exploring new areas, finding items, and farming mining resources. So on this framework, there can be infinitely many tasks that we can define, but we define 3,000 tasks for users, for the user of the MineDOJO to get started with. And this is one of the largest open source agent benchmarks. And then we implement a versatile API that unlocks the potential of the game. And this task provide various modes of observations, actions, and observations, including RGB images, like what kind of voxels you have, GPS, and then the user inventory where you can where users can save items, and then equip like swords or axes to do more complex tasks. And the action space includes like a movement, the basic movements, attack, and then inventory management. And then my dojo can be customized at every detail, such as terrain, weather, block placements, and monster spawns. So given this simulator, we introduced around 3,000 tasks. And in the first 1,500 consist of a pretty simple programmatic tasks. So this task can be very simple, such as like mine end resources, that's so that we can programmatically define success rate, success or failure pretty easily. And yeah, examples include like harvesting resources, learning to master a certain skills, and fighting various monsters. And all these tasks comes with the language prompts like harvest and needs of a certain resources or master a certain skill, etc. And next, we introduce about 1,500 creative tasks that are freeform and open-ended. So in contrast to programmatic tasks, where we can easily evaluate the success or failure, These creative tasks don't have a well-defined or easy automated success criterion. So for example, let's say that we want the agent to build a house. But it is pretty difficult to evaluate whether something is a house or not. And for example, there could be like multiple windows. This could be a house built out of wood. Something can be built out of stone. And this success criterion is very ambiguous. I mean, it is pretty simple and easy for us to evaluate, but it requires like our prior knowledge on what a house is that uh, that we experienced so far. So it's something that we cannot simply define automatically. And the only way to use this, evaluate this is using more complex foundation models, such as like um, something OpenAI developed like Click, or more complex networks like CAN to evaluate whether something is um, has a resemblance to a house. So for this, we offer 3D, sorry. So, and to create this kind of foundation models, there has to be, of course, like a lot of data sets, and then we provide three internet scale knowledge databases. And it consists of three components. The first one is like a YouTube videos where users play Minecraft for hours. And then Minecraft is a big very popular game, and then a lot of there's a lot of YouTube tutorials on how to do things on Minecraft, and then we use these kind of data sets, videos to create this data set. A second one is Wikipedia pages. So Minecraft is pretty complex environment, and then it requires a lot of like a diverse knowledge, and then the people, of course, the community created this Wikipedia page so that they can like look up and then learn how to do things. And then third one is Reddit posts and replies, specifically Minecraft subreddit, where you can just ask questions and get answers from experienced players. So so MineDOJO YouTube data set consists of about like 1,000,000 videos. That ranges about like 300,000 hours. And during this video, people talk about explain how what's going on in the video. And when we get the transcripts for it, it almost consists of about 2.2 billion words. Second, players can have compiled large Minecraft specific Wikipedia, and then we have about 7,000 multimodal pages that contain text, images, tables, and diagrams. So here is some example Wikipedia pages, and this is a gallery of all monsters, and their spawning uh, patterns and how the attack mechanism works. And you can see that it includes like zombies, witches, horses, bees, and interesting monsters. And also it includes like recipes to create various items. For example, to create, let's say this golden carrot that's on top of the middle column. You need about like, let's say 8 gold nuggets, and you need 1 carrot to create this golden carrot, which is pretty obvious. But yeah, all these tables explain how to create stuff. And the last thing is diagrams. So there's a lot of like things that you can create, and then it has a hierarchies as well. So let's say that we want to create something complex, and then it can start from simple like glass bottle, and then if you put water in it, and then it becomes water bottle, and then if you combine this with the nether wart, it becomes awkward. It becomes awkward potion. So yeah, so there's a hierarchy, and then you have to follow a certain recipes to create more complex items. Um, Yeah, and finally, the Minecraft subreddit is a pretty active one, and many players showcase their creations, ask questions, and get help. Or just you can be a troll and be goofy as well. And then we collected about 340,000 Reddit posts, and then it contains about 6 million comments and then the 500,000 images. So here are some example subreddit posts that shows how people use this subreddit. So on the right side, the question is, does anyone know why some of my wheat won't grow farming? And then it contains an image of probably underground farm. And then there's a small torch next to it. And then as you can see, the wheat only grows right next to the torch. And then the top voted comment was, there's gotta be the light and add more torches. So yeah, it's pretty obvious that the wheat need light to grow, and then the top comment pointed out that it needs more torches to grow more wheat. However, as this data sets are very multimodal, and then the MineDOJO is a multimodal framework, we need some sort of like a multimodal network to bridge the gap between different modalities. And then here's like in this first MineDOJO paper, we introduced the foundation model called MineClip. And the idea is pretty simple. So for our YouTube database, we have like a timeline video and then the associated transcripts. And these videos are sourced from Minecraft players, and then they usually explain what they're doing in the video. So of course, there are some cases where they just talk about random stuff, but in many cases, they just explain what to do, what's going on in the scene, and so on. So let's see, for the rightmost video, you can see that the user is killing a pig, and then the transcript said, as I raise my X in front of the pig, there's only one thing you know is going to happen. So it's pretty obvious that it's associated with the video. So using this kind of time-aligned data, we trained MineClip similar to OpenAI Clip, but instead of like text to image association, we create text to video association, and then train this using contrastive loss. So each modality goes through respective encoder. So video frames, image frames, that's consecutive go through video encoder, and then the text encoder encodes the text into sentences into several vectors, and then we can compute the inner product between these vectors, and then the computer score that ranges from 0 to 1, and then we try to make the time-aligned data pair to be 1, and then the rest of them to be 0. And intuitively, MineClip learns the association, and yeah, just evaluates how good the alignment between the text script and video are. And we can use this as an evaluation network or a reward function for an action. So here's an example of our agent interacting with the simulator, and then the task is sheep to obtain wool. Yeah, so agent explores, it generates like a video snippet, and then which can be encoded and then fed into the MineClip. And the higher the association, the larger the reward, or the larger the correlation, and then we can use this as a reward function for reinforcement learning. And then here are some of the demos we learned. Here are some of the demos of our agents performing some of the tasks. For instance, like milk a cow, hunt a cow, shear a sheep, and so on. You know, you can see that the agents were doing what they're asked to do. And For more details, please check out our website, MineDOJO.org. Where you can find a lot of like papers, videos, models, and samples from the knowledge base. And I'm going to switch to the second paper. Voyager. So this is an extension of MineDOJO, and then it's an open-ended embodied agent with large language model. So we saw that GPT-4 from OpenAI is a very intelligent system, and then it can write like long articles, very good codes, and have a pretty long conversation with people. And all of these require attention to details as long as like long horizon planning ability. And we wanted to harvest this ability, this long horizon planning capacity for GPT-4 for an open-ended environment, specifically MineDOJO. And then we wanted to combine this harvest this stability for learning an open-ended embodied agent. And we named it Voyager. So this is the first large language model-based learning agent that plays Minecraft for hours on end. The video here shows snippets from a single episode of Voyager. So it was spawned without anything, but it starts to learn skills, harvest items, fight monsters, until it reaches a certain goal, mine a diamond. And then, but it's not limited to that. And then it can do a lot more interesting tasks as well. However, the main central question of using the power of GPT hinges on our ability to convert the environment and the state of the agent into a string format. And if we want to use the power of the GPT-4. So GPT-4, I think they updated and then it can take like the image modality right now, but still language is the major data input source for GPT-4. And converting this open-ended environment that contains videos, RGB videos, GPS, inventory, and so on into string is a very important pipeline process to use GPT-4. And thankfully, the enthusiastic Minecraft community already built such converter that stringifies the environment as well as the agent's state. And it's called the MineFlayer. So this is a higher level API that's actively maintained to work with every version of the Minecraft template. The beauty of the MineFlayer is that it has access to the game state surrounding the agents, like the nearby blocks, animals, enemies, as well as like controls, such as handling movements, inventory management, crafting, digging, building, and so on. So basically, we have effectively a ground truth perception module that converts all these environments, RGB, everything into a textual beacon. And the key idea of the Voyager is to use code to control unembodied agents. So GPT-4 shows a quantum leap in the coding skills, and then we wanted to harness this skills to make GPT-4 to create MineFlayer code snippets. So here, for instance, we asked GPT-4 to create a function for combating zombies, and it reads function combat zombie, and then it first tries to find inventory item, sword, stone sword. And then if it has a sword, and then it's going to return the sword state. And then if we have a sword, then we are going to equip the sword on the hand. And if it fails to find the sword, then it awaits craft stone sword. And then all these functions are created by GPT-4. And we have a library of functions that this GPT-4 actor can use with. And then you can do this like, you can also, and then after it's equipped with a stone sword, it can also craft shield and look for and combat a zombie. But the code that GPT-4 writes sometimes isn't like always reliable, and then it usually doesn't get it right on the first try. So we developed this iterative prompting mechanism to refine the program. And then there are 3 types of defects that we can use to make this code better. So the first one is the execution error from the JavaScript interpreter. And then the second was the environment feedback, whether you are able to achieve the task or not. And another is like more meta, which is like a critically using our additional GPT-4 to think about like, well, what could have failed, like what could have gotten wrong, and then how to fix it. And then this, you can think of this as a self-reflection, and it can improve the code as well. So let's look at how Voyager does self-reflection to analyze the current task progress. So the first example, I'm not sure whether you guys can read at the back, but it's the first task is craft a spyglass. And GPT-4 looks at the agent's inventory, and then decides whether it has enough copper, but it's not enough M3. And second task is to kill 3 sheep and collect food. And then each sheep drop 1 unit of white wool, but it says that the inventory says that they have 5 logs, 1 wooden pickaxe, and then 2 white wool. Yeah, so we have 2 white wool and then 6 mutton on the inventory. And the task is kill 3 sheep. And the GPT-4 says that you have 2 white wool and then the 6 mutton chops, which indicates that you killed 2 sheep and then you need to kill 3 sheep. Success is false, and then critic says that to find another and combat kill to complete the task. So this kind of self-critic allows the self-reflection allows the agent to improve, evaluate the system and evaluate the situation, then how to propose solutions automatically. So let's say that we go through all these processes and we implemented 1 unit skill. And then we save it in this persistent skill library as a set of like an object, JavaScript codes. So this skill library can contain like functions for mining wood log, crafting stone swords, and so on. So, and then once you start from a simple task, like you first craft like an axe, and then use that axe to do more complex tasks, and then the actor can harness the previous tasks that we saved on the skill library to accomplish more complex tasks. So it's essentially like a self-improving knowledge base. And finally, we have yet another GPT-4 that proposes what task to do given its own capacity at the moment. So you can think of this as an automatic curriculum. And then this curriculum has an unsupervised objective. This is like unsupervised project, which maximizes the number of novel items that an agent obtains. So technically, this is very programmatic, but still, just by maximizing the number of novel items, or maximizing the number of skills that it can accomplish, we are making the GPT-4 to develop new skills, find new resources and so on. So you can think of this also as like a curiosity-driven exploration or novelty search in prior literature, but purely implemented in context. And second, it is like a situation-aware curriculum, because like, if we haven't learned more advanced skills, you have to use the existing skills to develop the next level skill, not the skills that's like far beyond the skill tree. And here are some examples of the situation awareness. It says that the biome is river, and then inventory, we have 4 items in the inventory. The first one is a sugar cane, paper, fishing rod, wooden pickaxe. And the GPT-4 says that since we are near the river and then has a fishing rod, it would be a good opportunity to catch some fish for food and experience. And then it created a task, catch one fish. And next one is pretty similar. So you have cat villager in the vicinity, and then you have, and then the hunger indicates that you have 0 out of 20, which indicates that the agent is starving. And the GPT-4 says that since the agent is starving, kill 1 pig to satiate the hunger. So after we put all these together, we have this iterative prompting mechanism that refines the program intelligently, as well as a set of skills that can act like a replay buffer. And finally, we have an automatic curriculum that acts as like a curiosity exploration or curriculum learning. So in the end, we do not have a neural network. I mean, the GPT-4 itself has a neural network, but there's no gradient architecture, and then this is purely done using intelligent system GPT-4. And then this allows the Voyager to self-bootstrap and perform continuous lifelong learning in this open-ended world. And then these are some of the tasks a Voyager happens to pick up along the way. We didn't pre-program any of this, and it's all Voyager's idea to like gather cactus, build base, and so on. And we've done a lot of systematic study for Voyager, and then here is some quantitative learning curve. So the x-axis is the number of prompting iterations, so number of GPT-4 calls, and then the y-axis is the number of unique items obtained by each agent. And we compare with 3 baseline: React, Reflection, and then the AutoGPT. And all of these are no gradient architecture that's built on top of GPT-4. So React is a pretty simple reasoning, has a pretty simple reasoning and acting loop. And then Reflection is built on top of React with self-reflection. And then we see that the both struggle to make progress beyond the basic wooden tools. And AutoGPT is a popular software where it can decompose a task into multiple smaller chunks, and then each accomplish task using chunked smaller tasks. And it combines React and Task Planner. And as you can see, it achieved like iron tool, but haven't reached any more advanced items. And finally, this is a Voyager. And then we are able to obtain like 3 times more novel items than the prior methods. And it unlocks the whole new tech tree significantly faster, from wooden to stone to iron to diamond pretty fast. And the blue curve is the evaluation study that we've done without the skill library. So as you can see, it plateaued after a while, and then so you can see that having a skill library allows access to higher tech trees and then accomplishing tasks much faster. And also here's a bird's eye view Minecraft map of how far each agent explored. And as you can see that some of the agents tend to get stuck in the local areas, whereas our Voyager were able to explore a much larger area. And finally, one limitation is that the Voyager has is that it doesn't support visual perception correctly. But with the GPT's new capability to process images, we might be able to extend it to evaluate more complex tests, like whether we built a library or something. And this is the Voyager's website, voyager.minedojo.org, and then we open source everything, including the MindFlayer connection, Voyager implementation prompts, and pre-trained libraries as well. And then this is the team. And then if you have any question, please send your questions to drjimven.ai@gmail.com. Thank you so much.